Pluto is a distant and covert, more humble planet that was once a piece of our nearby planetary assembly. However, advancing disturbing statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with dazzling exposure. They recommended that this viral world is on a potential intense trajectory with Neptune. Yet how might this, in fact, work? Also, what might be the results of such a titanic event? Are we seeing a flabbergasting, endless natural disaster? Or is there something different to this approaching, never-ending calamity? Join us as we examine the plausible results of a Pluto-Neptune impact. Pluto, a former planet that was later renamed as a dwarf planet, remains a subject of interest and concentration in the vast universe. As shown by ongoing studies by leading specialists, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which could represent a tremendous risk to Earth. But how is such an event even possible? Pluto's journey around the Sun isn't like that of any other planet in our nearby planetary system. It requires a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its abnormally curved shape, wandering broadly from the nearly round orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, which is tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is much more inclined compared to other planets. This inclination and eccentricity add layers of complexity to its orbital arrangement. One of the most intriguing aspects of Pluto's orbit is its convergence with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we might expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets whose orbits lie somewhat close to the ecliptic plane, Pluto's orbit sticks out with its steep inclination and eccentric shape. The mystery grew with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves calculating how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. For Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms non-synchronous libration and orbital precession, along with the VZK wobble, are important to this puzzle. According to astrophysicists, what keeps all planets in their orbits is non-synchronous libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is located about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from merging. Orbital precession, on the other hand, refers to the upward movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an extra layer of protection from potential impacts. Another key factor in this situation is the VZK wobble, named after three researchers, Zell and Kai, who studied how objects move in space. It involves the way three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This gravitational pull affects how they move. For Pluto, the VZK wobble helps us understand why its orbit near the Sun is so erratic. Despite Pluto's path seeming unconventional, this wobble helps keep it moving smoothly over long stretches. The VZK wobble shows that, although things in space might seem chaotic and erratic, certain patterns and rules keep everything in balance. These factors help maintain Pluto's orbit stability, ensuring it doesn't collide with Neptune or drift out of place. This three-body problem is key to understanding how these orbits evolve because of the way space objects pull on one another. Studying this helps us dive deeper into Pluto, our nearby planetary system, and even distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is actually unstable, with minor deviations in initial conditions leading to enormous differences over millennia. However, these quirks in Pluto's orbit have been found to maintain stability over incredibly long timescales. Observing this disturbance has been crucial. Later automated assessments have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit. Saturn also contributes. These studies show that Jupiter's massive gravity is strong enough to ensure that Pluto stays on a consistent path for a long time. So, perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These eccentricities are essential for maintaining balance and stability in space. Without these components, the solar system, as we know it, would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can reach a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of ongoing observation and research to better understand these phenomena. Place in the universe. Exploring the profundities of space frequently drives us to go up against the peculiar nature of heavenly bodies. Also, Pluto's circle is an ideal illustration of the flightiness of orbital turmoil, which alludes to the touchy reliance of a heavenly body's circle on its underlying circumstances. This is plainly outlined in Pluto's case. This implies that even slight changes in the Bantam planet's situation or speed can altogether adjust its long-term circle. Utilizing programmatic insights has been enormously useful for researchers in sorting out how Pluto moves in space. These reproductions utilize complex science to show how Pluto and other space objects, like Neptune, pull on one another. By tweaking little subtleties in the reproductions, space scientists can see how even minor changes can extraordinarily influence where Pluto winds up. In the late 1980s, these recreations showed something interesting about Pluto's circle. In spite of having highlights like non-simultaneous libration and orbital parade to keep it stable, Pluto's circle can in any case be sporadic and erratic. Assuming you start with even a little distinction in where Pluto is or the way that quick it's moving, its circle could wind up looking totally different after only a couple of years. However, indeed, even with this mayhem, Pluto's circle stays stable over extremely significant stretches, like billions of years. This basically implies that Pluto's excursion around the Sun has a kind of order to it, even though it appears violent from the beginning. Foreseeing divine occasions, particularly at the point when they involve sporadic circles like Pluto's, is a tremendous test. The inborn unconventionality of these frameworks implies that drawn-out conjectures are frequently loaded up with vulnerabilities. While numerical models give amazing instruments for understanding and anticipating the future ways of heavenly bodies, they additionally highlight the limits of our prescient capacities. These models rely intensely upon the precision of starting circumstances, and any little error, mistake, or contortion can prompt tremendously various outcomes, making exact expectations an overwhelming undertaking. Besides, the tumultuous nature of planetary circles, like Pluto's, helps us to remember the ever-changing dynamic nature of the universe. While we've taken enormous steps in understanding space, Pluto's case reminds us how much our insight into the universe still stays restricted. Understanding the gravitational impacts of the Goliath planets on Pluto's circle gives significant insights into the more extensive elements of the planetary group. It shows how the presence and position of each planet can fundamentally influence the steadiness and direction of different bodies inside the framework. So why are driving astrophysicists, as of late, raising worries about an expected accident between Pluto and Neptune? In spite of every one of these complex powers attempting to forestall such an occasion, Neil deGrasse Tyson, a conspicuous astrophysicist and a vital figure in advancing cosmology, offers a remarkable viewpoint on the secrets of our nearby planet group, particularly the interesting instance of Pluto. Tyson, known for his job in renaming Pluto from a planet to a bantam planet, gives canny perspectives on the evolving idea of heavenly mechanics and the public's advantage in the dismissed domains of space. Tyson's position on Pluto's renaming depends on the steadily extending information on our nearby planet group. He sees the renaming not as a diminishment, but as a significant change in alignment with our developing comprehension of the many bodies circling our sun. Tyson's way to deal with divine specialist mechanics is one of persistent learning and change. He sees the intricacies of circles like Pluto's as an indication of how much there is still to find in space. The interest with these inquiries keeps space exploration so intriguing. Anyway, regardless of Tyson's certainty, his considerations on Pluto's possible contact with Neptune spread out a different picture. His interest about the fate of Pluto's circles suggests that there could still be a few additional mysteries to uncover. Will Pluto slam into Neptune? Or is this simply one more moment of disarray in the continually evolving universe of space? Just time and further examination will tell. Until further notice, we are left with a more profound interest in how little we still know about our own solar system. We continue to contemplate these heavenly peculiarities with the expectation of uncovering a greater amount of the secrets that lie beyond. The possibility of a Pluto-Neptune crash raises one more question about the baffling and dazzling universe in which we exist. The potential for a crash between Pluto and Neptune raises entrancing issues about the dynamics of the solar system, as it challenges conventional understandings of planetary stability. The possibility that two heavenly bodies with such immeasurably unique properties could impact is both disrupting and charming, particularly taking into account the ongoing relative strength of their circles. Given that Pluto is situated in the external ranges of the planetary group, nowhere near the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a crash would be colossal for our comprehension of gravitational communications and the development of the planetary group. To grasp the dynamics of a potential impact, one must first consider the construction and properties of the two planets. Pluto, regardless of being a bantam planet, contains an assortment of components and mixtures believed to exist in a frozen state because of the extreme cold of the external nearby planet group. Its surface is shrouded in nitrogen ice, and it has an atmosphere made largely of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a monstrous gas planet, is essentially made out of hydrogen, helium, and other lighter components, with a deep, thick atmosphere. An impact between such disparate bodies would radically influence their design and conduct, possibly making an event apparent across huge distances. What makes this theoretical impact especially enamoring is the impact of other planets and bodies in the planetary group. While Neptune's gravity plays a prevailing job in keeping Pluto's circle stable, it isn't the only variable having an effect on everything. The presence of Jupiter, the largest planet in the planetary group, is another key component. Jupiter's tremendous mass, strong gravitational field, and gravitational pull provide a stabilizing impact on Pluto's circle, keeping it from wandering excessively far into Neptune's area. Also, Saturn's gravitational impact further confounds the dynamic elements of the external planetary group, making it far-fetched that a devastating occasion will happen between Pluto and Neptune.